All right, let's get started. So welcome to lecture 2 of robotics. So we can start with some logistics. We will do team assignment over the weekend. We had some issues with registration, but hopefully that'll be done this weekend. We'll assign everyone teams. It's your job to come up with a fun name and send it to us, and then we will set you up with each team gets their own GitLab repository and their own car, their own workstation. We'll set you up with that over the weekend, and so you can come in any of the office hours next week to get your equipment. There's a homework that will be due on the 17th, but it's extremely easy. It's just going through a bunch of instructions, so there's not really a lot to do. So don't worry too much about it. But it's more to get you familiar with the ecosystem. So those were logistics on my end. Any issues that came up for anyone else that we should discuss? Any issues with the knowledge survey? No? Good. Okay, sweet. As I promised last time, I will start with a little bit of a history lesson and some videos. So, the word robot was coined in 1920, I think, by this Russian author. And robots are supposed to be creatures that do unpleasant labor. But since then, we've come a long way. And so I want to give a little bit of perspective on different types of different generations of robots that we've had and where we are now, right? And so, the first set of robots that we had, this was something called the Unimate from the 1960s. It was like one of the first industrial robots by these people, Devol and Engelberger, and they were putting it in GE plants and Honda plants and a bunch of car factories. And from there was a robot called Shaky, which was at Stanford, which was supposed to navigate around the hallways, getting to particular places, around unknown room configurations, dealing with uncertainty. And it doesn't look like a lot, but that robot led to the development of a lot of the algorithms that we're going to study this quarter. So that's also from the 60s. So maybe we should update our curriculum. After that was the Honda P series in the 90s from Honda. And so if you all have seen the Asimo and those kinds of robots, these were the predecessors for the Asimo. And that's kind of what's led to modern robots today. And so that's a little bit of history. You should look it up. All of these are super cool robots. But then the second round of robots that came about was from the DARPA Grand Challenge. So the DARPA funded a challenge where they asked a bunch of teams to drive through the desert at high-speed autonomous.
Welcome to the DARPA Grand Challenge. The objective, create a self-navigating autonomous vehicle that can safely drive 132 miles through a harsh desert environment without human intervention. Yes, these are robot cars, and if you've ever wanted to see the future, take a good look, because it's right in front of you. The technology we see here will be used in the military within the next few years, and eventually, robots like these may be taking you to and from work. But it's not easy. 43 teams from around the country began with dreams of building a robot capable of conquering this course. Only 23 teams earned the right to run in the $2 million DARPA Grand Challenge final. For qualifying teams, information about the event is held in tight secrecy until race day. It is only then that they will receive details about the course. At 4 a.m., just 2 hours before their scheduled run times, competitors are informed that the route will stretch 132 miles over rugged desert terrain. With that information now in hand, teams rush to program their vehicles to navigate the thousands of GPS waypoints they will need to pass to successfully complete this challenge.
With robots closer to early 2000s. And now the robots today are much cooler. So these are the everyday robots from Google, where they're driving around these micro kitchens, trying to pick up objects, put them in places, retrieve particular food items, and so on. And they do it from language, and they do it in pretty general settings around people. And I showed all of you these about dynamics, where they have these Atlas robots.
My tools again.
And dance and jump and manipulate and do lots of stuff that looks amazing. the key thing to note here is that a lot of these are extremely cherry picked and that they're controlled environments and they do great with the problems, but they're not quite, but it's still amazing. But it's important. So if you go from the 1960s when we had, shaky robot navigating to the moon, it's pretty amazing. Right. So, some robots in industry which I think are cool to look at are these are some Fanuc robots in a car plant where they're assembling car parts and doing precise motion at scale on millions of pieces, right? And so these are pretty commonplace in most car factories, but they're harder to do for small parts and things like that. The caveat here is that the factories are extremely controlled, right? And so if you have people messing things up, it doesn't really work. So it's extremely controlled, but it's still amazing. This is a video from Waymo self-driving car.
We're about to see how it all works and what it feels like to ride in our car.
But you can see that it forms a map of the world using a LiDAR.
Waymo uses LiDAR,
Tries to make
which
decisions
sends out
about where
millions of
people are,
laser
where
beams
other cars are, reason about
build
where
a
they're going to
detailed
go,
picture of the
and
world
do
all
pretty high-speed
360
maneuvers.
degrees around it.
Relatively.
It also uses radar
Generally,
to
they've
detect
been
how
pretty
far away
successful in
objects
San
are
Francisco
and their
and
speed.
nowhere else.
And
So
high-resolution
I think there's
cameras
still a lot more
detect
to be done
visual
about
information, like
generality.
whether a traffic signal is red or green.
But still much better than we were
Then
even a couple of years
combines
ago.
all that data to understand the world around it. For example, in this fraction of a second.
And then we looked at the Boston Dynamics one, and this is another video I really like from OpenAI.
We're trying to build robots
Have a
that learn
robot
a little bit like humans do by trial and error. What we've done is train an algorithm to solve the Rubik's Cube one-handed with a robotic hand, which is actually pretty hard even for a human.
Should I mute it or?
We don't tell it how the hand the cube in order to get there.
Okay, I think that's good. Yes. Good. So the goal here is to manipulate this Rubik's Cube, solve it using a robot hand, and they actually trained this with reinforcement learning and simulation, and then they transferred it to the real world, and it was like moderately successful, but it showed like a bunch of things that we didn't think we could do ever before, right? And it's what makes dexterous manipulation hard is that you have to make and break contact in different ways that are like difficult to do in a hard-coded fashion, right? Because every cube is different, the friction is different, the contacts are different, it's hard to model, and so that's what makes these results pretty cool. All right, so I think that's most of the results I want to cover. And now you're thinking, okay, I want to make these robots. It's a big mush. I don't really know how to, even approach it. And so what we're going to try and do today is try to think about a framework that we can use to think about how to build robotic systems, right? So we've looked at a bunch of interesting, useful robotic systems. What we're going to try and do today is try to think about what the design methodology is going to be for building new robotic systems, right? So what we're going to try and do is we're going to, think through the steps we would take to go from tabula rasa, we don't have anything, to the design of the robotic system. And then we're going to spend the next 10 weeks actually implementing said robotic system, right? But let's try and lay out the structure of what the pieces are for a robotic system, why those are the pieces, and think through like the design of a general purpose system. So we're going to do race cars, but to motivate what we want to do, let's think about helicopters instead, right? It's like a similar type of system. The next 10 weeks are going to be devoted to race cars, but today let's think about helicopters, right? So what we want to do is we want to autonomously navigate with a helicopter. So we have this autonomous helicopter equipped with a bunch of different sensors. So you have a LiDAR, GPS, camera, a bunch of other sensors. You have autonomous control over the different pedals of the helicopter, and you want to accomplish a mission, right? So you want to take off somewhere and you want to land somewhere else, deliver a payload, do it safely under uncertain conditions, without like having a human operator. And so all you really want to do is upload a flight plan of where you want to go. You don't know exactly what the obstacles are going to be. The world keeps changing, the weather keeps changing. the terrain often changes, right? And so you want to figure out how to navigate around these obstacles, not crash into rocks, and get to where you want to go, even under uncertainty, under different weather conditions, under different wind, and so on. Right? And this is like a several million dollar helicopters. You really don't want to crash it. Right? And so that's the kind of problem we're going to think about, which is how do we take an autonomous helicopter and then figure out how to control it to go from point A to point B under certain conditions. Right? Does that problem make sense? Yeah. All right. So generally, you're going to start somewhere. You have takeoff. You're going to have a bunch of obstacles on the way, which we're not going to know exactly. Right? You're not going to know exactly what the obstacles are a priori. They're not going to be on a map of the US. And then you know where you want to go, but you don't know exactly what the conditions are going to be when you there, right? So you might want to, you might want to land here, but there's an obstacle, so you might want to land nearby. So you want to start somewhere, get to the target while respecting constraints of fuel, power, not hitting anything, obeying flight rules, right? And so you want to, successfully accomplish this mission autonomous, right? It's not that different from a race car, it's just one flies and the other does. Okay, so to kind of state our problem more clearly, we are given a starting latitude and longitude, goal, latitude and longitude, a list of no-fly zones, so things that we can't go into, right? A terrain map roughly of the US, but that is not necessarily accurate. And then we're given access to some number of sensors on the robot, each of which is somewhat noisy. Right? What we really want to do is we want to figure out how to get from point A to point B while minimizing time, not crashing, not running out of fuel, not violating any federal laws. Right? And you want to make sure that you do it in a way that doesn't make anyone feel unsafe and doesn't cause disruptions to other vehicles and all of those things. Right? So that's the problem statement we're going to think about. And let's think about how to tackle it, right? So the first thing we're going to think about is how to tackle it the model-based way, right? And then we'll cover the model-free way. So when I say model-based, what do I mean, right? So let's start by thinking about the problem from first principles, right? So it's going to start from what are the inputs and outputs of the system, and then you're going to walk me through how to do it. So you have a helicopter, you have some number of sensors, you have a laser, right, which tells you how far away things are. You have a camera, you have a GPS that approximately tells you where you are. And what you want to do some black magic, and you want to output some set of actuators, which is like the lever and the pedals and the stick, which control your helicopter. And now I want to figure out how to, given the constraints of my system, start from those sensors, output these actions. Okay. So that's the inputs and outputs. How would you approach? Yeah.
Well, I guess that rules the basics or like front end, right? You get the sort of like the right sort of like desired like state vector, the actual like helicopter, right?
Yep.
Use some kind of controller, like or like a P controller, actually move the actual action layer, sort of get toward that desired state vector.
Right. So, remind me of your name.
Okay. Gavin?
Gavin. Okay. Gavin is saying we want to use something like a PD controller, which tells you, we haven't really covered what PD controllers yet, but let's assume it's a controller that says you want to go from point A to point B, and it helps you figure out how to get from point A to point B while compensating for errors. Right? So I think that is part of the solution, but it's not the entire solution, right? Because we want to figure out how to navigate around obstacles. We want to figure out how to change our plan globally. We don't actually know where the robot is in the world. You don't know the state of the robot, right? And so PD control is a part of the solution, but there's other elements that we need to go from raw sensor readings to doing something like PD control, right? And so yeah, that's certainly part of the solution. What are other things that we want to start? Other things we know about this system, we have a helicopter. We know the maps of the world and we know those kinds of things. What else would we do to approach it? My thoughts? Yeah.
for like the first step, is having like a general state estimator based on what their inputs.
Right. So, let's figure out where state estimates fit into the whole thing. Right? So let's start by defining what I'd call a world model. So we want to start by using our knowledge about the system, right? So we know this is a helicopter. We know how helicopters work. We've like studied physics, right? So we know how helicopters work. And so we want to be able to use our prior knowledge of the system. We know the rules of aerospace. We know we can't navigate into certain regions. We know that if you collide with things, they're bad, right? And so we have a lot of prior knowledge about our system. And so we're going to try and use that prior knowledge about our system to design this control, right? So what we're going to try and do is we're going to take all of our knowledge about the system and encode it into something we call the world model, right? Or a model. And this model is basically figuring out how the world works. Right? It's saying, it encodes all of our knowledge about the rules of the world, right? So like if my helicopter was here, I applied some controls, where would it be? Right? Or I can't go into this part of the world because I'll get a big negative cost. Like all of that is encoded into a world model. Right? And so world model is basically anything that encompasses all of our knowledge about the system. Right? But a world model by itself doesn't actually necessarily connect to the actuators and sensors, right? So you need to figure out how to take the sensors, make it appropriate to go to the world model, and then get the outputs of the world model and actuate the system. Okay? So what do I mean by that? I mean by that we take our sensor readings, we take raw laser readings or raw camera readings or raw GPS, and we convert it into something that is compatible with our knowledge about physics, our knowledge about the world, right? And now once we have a world model that tells us how the world changes when you take actions on it, right? And once you know how the world changes, you can decide how to act, right? And so the way this whole loop is going to work is you're going to start from sensor readings. You're going to convert those sensor readings into a format that is compatible with our knowledge about the world, right? This is our world model. And then once you know how the world works and where you are, you can figure out how to act in the world so that you accomplish your objectives, right? And so the reason this is called the model-based approach is because you're using a lot of prior knowledge about it. Right? You're using knowledge about physics, you're using knowledge about aerospace rules, you're not just going blind into the system, right? You're using knowledge about how the world works. But in order to make this compatible with the assumptions that we had, right? Which is no one tells you exactly where you are, you just have raw sensor readings and your actuators are noisy, right? You have to figure out how to convert sensor readings into something that is compatible with your world model. That's going to be something we call state estimation, right? And then you have to figure out how to take your world model and figure out how to act with it. And that's going to be something we call planning and control, right? And so the loop we're going to take is sensors, the state estimation to world model to planning and control, actions, repeat, right? Does that make sense? Any questions? Does that seem like a wildly incorrect model of the world? No? Okay. So, as I said before, it's like we're gonna study these three problems of state estimation of where we are in the world, right? We're gonna figure out how to model our system, right? What is modeling? And then we're gonna figure out how to actually act in the world. So we're gonna figure out how to plan and how to do control. And I'm gonna define all of these terms, right? But intuitively, they mean, how do we decide where we are in the world? How does the world work? And then how do we act to accomplish the desired objectives? Right? Okay, great. So given this, model of the world, let's start by, or given this, pipeline of robotic control, right? This is like the general template of design. Let's try and like get more concrete, right? These terms are still very abstract. Let's try to make them more concrete. So let's think about modeling, right? What does modeling mean? So essentially what I mean by modeling is that you want to figure out, given an estimate of where you were in the world, right? And some set of sensor readings and some set of controls, where are you going to be in the world next, right? And so essentially a model is something that uses our knowledge of physics, our knowledge of the particular domain, etc., to take your previous state of your system or your previous estimate of state of your system, and then figure out what your next estimate is of your system state should be. So essentially what a model is going to do is it's going to figure out how the world works. And what I mean by that is we have certain variables that you want to model, right? The variables you want to model are things like the position of your helicopter and the speed of your helicopter. What is the payload distribution like, right? You might also want to model things like what is the wind conditions today? Or you might want to model different things that are not necessarily known a priori and maybe changing throughout your control sequence, right? And so those are the things that you want to model. What you're going to figure out is how do they change, right? So you're going to try and figure out how does the position, the speed, the payload distribution, the wind, the effect on other vehicles, how do they all change? And the way we're going to use that is we're going to use our knowledge of physics. We're going to use our knowledge of how aviation rules work. We're going to use our knowledge of other aircrafts, right? And so we're going to encode all of that into a model. And you think of the model as just a mathematical object that takes in previous estimates of state and what action you're going to take and gives you the next estimate, right? And to do that, we're going to use all of our fancy work that the physicists have done for the last 200 years, right? And then besides just figure out how the world works, you also want to accomplish particular objectives, right? So you want to get to a particular location, you want to avoid some obstacles, you want to satisfy certain constraints, right? So let's say you had, a vat of dangerous fluid on board, you didn't want to spill it, right? You are going to incur a huge cost if, the pitch of the helicopter changes, right? And so all conditions and constraints on your mission are going to be encoded into something we're going to call a cost or an objective function, right? And some people choose to put this with a model, some people choose to have it separately, but it kind of doesn't matter. It's like our prior knowledge about the world. And so we're saying, we're going to model some things, we're going to figure out how they change with domain knowledge, domain expertise. And then we're going to have some costs. And our goal is to figure out how to minimize that cost while satisfying constraints. Okay. Now, is it easy to do this? What are issues that might arise, right? Like what might make this difficult or what might make this non-trivial? Or should we all just program helicopter? Yeah.
Is for the time that you create the model, that the model, a lot of things will be different.
A lot of things will be different.
Or outside of
Right.
like what you might expect.
Right. So it's a problem often called model misspecification, right? So your model is always going to be wrong. And so there's like this quote that this statistician had, George Box, saying that all models are wrong. Like every single model you ever make will be wrong, right? Unless you model things at the atomic level, and even then they're going to be wrong. But that doesn't mean they can't be useful. And so what we have to figure out how to do is to deal with the incorrectness of our models while still making them useful. So for instance, your knowledge of physics is not going to be perfect. You don't perfectly model turbulence. Your estimate of state is not going to be perfect. Your cost function may not be perfect. And so you have to deal with noise in the whole system. So that's primarily the issue with modeling, is that models are going to be wrong, right? And the way we're going to deal with models being wrong is we're going to make everything probabilistic, right? So we're going to have uncertainty and we're going to do planning that is robust to uncertainty. And that's how we're going to deal with these incorrect models, right? But the important thing to remember is that we're going to have a lecture about models. It's going to be a full 1 hour lecture on models, and all of those models are wrong, right? And the important thing is that they're wrong in a way that's useful. Okay, but essentially, the system we're going to consider, the race car, is much simpler than a helicopter. And so we can actually write out the world model very easily. It's still going to be a wrong model, but we're basically just going to work out some simple physics, and that's going to give us our world model. In the helicopter case, you have to model turbulence, you have to model wind, you have to model other things. Okay, but the other thing to remember is, like, a lot of times what people refer to as a world model is a simulator, right? A simulator and world model are not that different. So when people have very accurate simulators, that's essentially a world model. It's encoding all your knowledge of physics, all your knowledge of, how the world works. into something that you can simulate and render and figure out what's going on. Okay. So that's the first step of the process, right? We have modeling. So we've started with sensors, we have actuators, and we have a model. But we have no real way to stick our sensors into our world model, and we haven't really discussed how to take our world model and produce actions, right? So I don't really care about modeling. Who cares about modeling? I care about sensing and actions, right? So the important thing about modeling is that it has to connect to raw sense information and has to output things that do raw planning and control, or raw actuation, right? You have to control the helicopter. So the next thing we want to think about is, let's say we, we assume that we knew, we assume that we knew where everything was. Yeah. So we knew what the position and the speed of the helicopter is. We've got an estimate of state, right? So you know where everything is. You know how the world works, right? What you need to figure out is how do you act in a way that that minimizes your costs or satisfies your objectives while satisfying your constraints, right? And so that's what we're going to call planning and control. So the planning and control is essentially how do we use our world model given an estimate of state to accomplish desired objectives, right? Now, there's two different words here. There's planning and there's control. And they're very related, but they're slightly different. So what is planning? Planning is figure out how to act in a coarse way. And control is figuring out how to act in a really fine-grained way, right? So when I say coarse way, I mean that, you want to go at the like 10-meter resolution, your helicopter is flying through space. You want to figure out how to act in a way that doesn't hit obstacles, and doesn't go into no-fly zones and satisfies the constraints of not, spilling the dangerous liquid on board, right? So the problem of planning is given a start configuration and an end configuration and constraints of your system, right? How do you figure out the sequence of configurations that take you from one place to the other without hitting any obstacles? Or hitting any obstacles is one instantiation, there could be other. So, that's what we're going to refer to as planning. And what control is going to say is, okay, imagine that planning gave you started here, right? Planning gives you a bunch of configurations along the way, right? That says, okay, this is the next place you should go to in 10 meters, right? And tells you what the next position, next velocity should be. And what control is going to do is going to take that next desired position, next desired velocity, and convert it into, motor torques, or how much to press the pedal, or how much to, turn the rudder, right? Controls of your system. And the important thing is that it's at a much finer grain resolution, right? And planning is not so concerned with dealing with the nitty-gritties of your system, right? It's trying to figure out how to like obey the constraints of your system, satisfy your objective, but it's not concerned with the disturbances along the way. Whereas control is really concerned with, okay, you're going from here to here, there's going to be some turbulence along the way. How do you stabilize at the short term? And so planning and control are not that different. They're just operating at different levels of resolution, right? And so the things that you think about when you're thinking about planning are very global, right? And so that's why often planning methods are very discrete, where things you think about in control are much more local. And that's why you think about much more continuous ways of doing control, right? But that dichotomy is a little false. Okay, so to kind of recap what I just described, planning is an optimization problem where you want to search over a sequence of actions that minimize a particular cost function or optimize some constraints using our world model, right? So the planner needs to use the world model because the world model tells you how the system can move, right? And then you want to make sure that you're not violating constraints, like you're not hitting anything, you're not spilling the liquid and so on, right? So you're trying to figure out, okay, this is my helicopter, I wanted to get somewhere while satisfying constraints. How do I do so while obeying my world model, right? So a question there is, why is this hard? This seems easy, right? It's like my helicopter here, I want to get here, just draw a straight line between us. It seems pretty simple, no? What makes planning hard? Yeah. Yep. And when you're implementing the option, maybe to become like physical physics parameters or different embodiments, the error might be like deviate a little bit. And then as you are going through the entire cycle. Okay. That's a great point. So the point is about compounding error, right? And compounding error when you mismodel the system embodiment or the system physics or something like that. That's probably you're going to deal with much more in control, and control is going to do stabilization. What makes planning really hard is often that the system is not holonomic, right? We talked about holonomic systems last time a little bit, but it's not like your system can, it's not like a helicopter can just translate its space arbitrarily, right? The helicopter has to obey the laws of physics. It has to travel along particular trajectories, right? And that is not like a low dimensional system. It's a high dimensional complicated system. And so actually figuring out even the trajectory that is feasible, right, is very difficult. So you have to figure out something that is kinematically and dynamically feasible. So kinematics means how does the system configuration change, right? So imagine you have a robot arm, you like have to figure out which things are valid configurations of your arm. And then dynamics is how does force affect everything, right? And so you have to figure out a set of configurations that is kinematically and dynamically feasible. And that's what makes planning hard. It's a little, I think the 2D image is a little misleading, but think about it in like a 10-dimensional space, and then everything becomes much messier. So that's what makes planning hard. Does that make sense? Everyone following that? We will have a planning homework, and so you will see exactly how hard it is. But take my words for it being hard. And control is really about dealing with compounding error, dealing with misclassification, right? So we talked about how our models will be wrong. If our models are wrong, then our controls will be wrong. Right? If our controls are wrong, then if you don't stabilize your system, you will like fly off and hit a wall. And so what you have to do is you have to do feedback. So you have to take, you decided you're going to take some controls in the world. You acted, it didn't go according to plan, and you have to replan so that you can deal with that error, right? And if you didn't do that, if you ran the system without doing control, without doing feedback, you will have an accumulation of these mistakes, right? And you more and more and more you accumulate, the more likely you are to go off track. And so you made a plan, you're trying to follow the plan, but the world is not the way you thought it would be. And so unless you do feedback control, you will never actually accomplish it, right? Does that make sense? So what you would see with your race car, for instance, is that you can command it a series of motor torques, and you try to play them, and it will not do what you expected. Right? Whereas if you do feedback control, every time you make an error, you recognize that you've made an error, and then you try to correct it. Right? And so the whole essence of control, like most of control, is really about stabilizing your system. And stabilizing your system just means trying to follow the path that you want to follow. Right? So that's the essence of feedback control. And so we'll cover a few different things for feedback control. Right? But planning and control together give you behavior that you want. Right? Control is often very local. I can't figure out how to navigate around the UW campus just with control. And planning is very global, but I can't actually execute it without control. And so they go hand in hand. Right? You can't do one without the other. Great. So that's kind of what control is. And so we started with the world, we started with nothing. Then we added a world model, right? And we said, okay, world model is great. Assume that we knew where we are in the world. Then how do we decide how to act? Right? And we've decided that we're going to act at two levels. We're going to do planning and we're going to do control. Planning is global, control is local. Okay. So why is this not the end of the story? What makes this hard? Why does this not just control our helicopter? Are we done? No? We talked about world models, we've talked about planning. But what is the last piece we need? It's on the slide. Actuators, yeah, that's a good point too. So I guess it really depends on how you do control. But typically, when you're doing control, you're going to try and take a desired position, and then control is going to convert your current position and your desired position into signal for your actuators. Right, so for instance, you're gonna output torques for your motor or currents for your motor, or how much to push the levers and so on. And that's often that is like wrapped up into control. But the line is a little bit blurry. But yeah, it's a good point. So how do we define and use actuators is important. How do we define and use sensors is important too. But the last piece that we really need is we need state estimation, right? So we've connected the dots from a world model to control, but we haven't connected it to sensors yet. Right? So we've said, if I knew where everything was in the world, I would be good, right? So far we've tried to do control and planning, assuming that we knew everything about the world, and we figured out what commands to send to our actuators. Yeah? But we don't, sadly, alas. Right, so all we know is like noisy readings about the world. We don't exactly know where we are. As I discussed last time, you have a race car in a building, you don't know where it is. Right? And so you have to use your senses to figure out where you are in the world, and not just where you are, but what are all the variables that you need to seed your world model. Right. So for instance, you might want to know what the wind is to figure out what the wind speed is to figure out what parameter to feed into your model, right? And that's a prognostic estimation. You want to estimate what the wind speed is going to be, right? So it's not just position and orientation, it's like anything that you need to seed your model, you have to estimate. You have to estimate it from sensor. Okay, so the problem with state estimation is to say, you want to figure out what all these things are that your world model needs, right? So you want to figure out where is the robot, what is its position, what is its velocity, where are the obstacles in the world, what are the no-fly zones, where are the other aircrafts, what is the wind speed, right? And you want to figure them out from these noisy sensors. If you have used even a simple depth sensor in the real world, it's just full of noise. It's messy, right? So what makes this difficult is that there's noise in the system. So the first thing that makes this problem challenging is that you have a large amount of information, right? So let's consider this particular mission, right? And you're flying your helicopter through space, you're shooting your LiDAR at the ground, and you are running your GPS and your barometer and everything else. You have 10 different sensors, right? Each of those are giving you some different information. And you have to figure out how to make sense of all of this information, reconcile them with each other, right? Your GPS might be telling you something, your LiDAR might be telling you something else, your barometer might be telling you something else, right? And you have to figure out how to deal with all of that information, figure out which thing is important, and then use that to estimate your state. Right? So you have to deal with a large amount of information. So this is often something you'd call sensor fusion. So you have different sensors, you want to fuse them to have an estimate of state. So that's the first thing that makes it difficult. And the second thing is difficult is that your sensors are noisy. Now they're noisy because you were cheap and you bought a cheap sensor, or they're noisy because you're flying through a snowstorm. Or they're noisy because of natural reasons. Let's say you're trying to detect a transparent object, right? A depth sensor is going to be really bad with transparent objects. If let's say you're flying through a snowstorm, your laser is going to reflect real weird of a snowstorm, right? Because of the nature of your surface. And so depending on the conditions you're in, your sensor readings can be more or less noisy, right? And if you just trusted them as is, you would be just totally screwed. And so you need to deal with that noise, and you want to maintain uncertainty in a way that makes you safe. Okay. So what we're going to do, the way we're going to deal with these noisy sensors, lots of information, we're not going to figure out an estimate of the state, which is a point estimate. We're not going to say this is where we are in the world. We're instead going to estimate a belief over state. Right? So we're going to say, I don't know where we are, but I think we're here. Right? So it's like, I could be here, I could be here, I could be here. You're going to estimate a probability distribution over where we might be in the world, right? And depending on how accurate your sensors are, that probability distribution will be more or less peaky, right? So if my sensor readings are extremely accurate, my belief is going to be really narrow. If my sensor readings are very noisy, my belief is going to be wide, right? And so what you really want to do is you want to be probabilistic, right? And so most of this course is really about being probabilistic, right? And so the goal here is you want to estimate what your state is going to be, and then you want to use your estimate in planning, right? And so when I say you want to use your estimate in planning, you want to not just take, the mean of your distribution, you want to be robust under uncertainty, right? Because you believe you could be anywhere in this distribution. You really don't want a catastrophic worst case if you're not at the most likely place, right? And so a lot of the planning and control methods we're going to think about are how to use that noisy estimate of state and how to plan under uncertainty.
This might just be because we're looking at the chart, like the school chart with the different things, but like what exactly is the relationship between planning and control and the estimation of state? Because in control, you need state to like figure it out, but then also you're kind of in a new state because your control takes you elsewhere. So do they work like?
They work together, right? So it's like planning and control are basically optimization methods that say, given your current estimate of state, like what is the series of actions that you take to accomplish your outcomes, right? But to see that optimization problem, you need to know where you are in the world, or you have to have an approximation of where you are in the world. And so the way that the loop works is that you take your sensor readings, you seed an estimate of state, and then you solve a planning and control problem given that estimate to figure out where to go next, right? And so you can't do like state estimation is it does the specification of what planning and control problem to solve, right? So you can't solve it without that. Does that make sense? Okay, so we've we've put together all the pieces of our system. We've said we start from sensors. We've done state estimation, or we've talked about how to do state estimation. So we're going to figure out where we are in the world. We're going to stick where we are in the world into a world model, which will tell us where to go. And using that world model, we're going to do planning, we're going to do control, it's going to give us actuators. We're good, right? What might be missing? Like what have I not covered? Or is this the grand vision of robotics that we should all follow? What are some things, even if we are still model-based, like what are some things that might be necessary in a production robotic system that I haven't covered here? Yeah. Maybe estimating error, yes. Estimating error, having some confidence. Part of that is in state estimation, but even when you're doing control, you want to have some estimate of the error. That's good. That's a good point. One thing I haven't mentioned here explicitly is safety, right? So you can do control, that's great, but most production systems will have a safety layer, right? You want your helicopter to drive around. If it's about to hit something, you better not friggin' hit it, right? Like, most systems will have a safety layer over here, right? And that's super important to run these systems. And most systems will kind of update their world model with experience. And so they're going to try and use data to learn better world models. And that kind of completes the picture of at least some production systems. There's obviously more complicated things, but does that make sense as a rough architecture of a robotic system? Right. Right. So we'll go from here to race cars, right? The goal is to do race cars, not helicopters, since we don't have any helicopters. If we succeed or not, only time will tell. And so, we have 10 more weeks for you guys to figure out how to control these race cars. But before we end, in the last 5 minutes, I wanted to discuss a different way of doing control, right? We've talked about the model-based way. And the reason it's model-based is because we took our knowledge about the world, we stuck it into our system, right? It's right in the middle of it. But in what cases might this be hard? Yeah. And the states are not so low dimensional, yeah. Right. And also not fully observable, right? Not fully observable, and not low dimensional. Good points. What other situations might make this hard? Yeah. The world might change a lot. The world might change a lot. Exactly. Another way of maybe putting that is when the world is extremely diverse, right? It's like if you have to deal with a different object every day, who's gonna model it, you know? And so in lots of cases, the model might be extremely hard to specify, or it might be so uncertain that it becomes unusable, right? And connecting with perception is easy in some cases, like a helicopter, but let's say you're deployed in a household kitchen environment, it's not really clear where everything is, and it's not clear how perception connects to everything. And so in those cases, it might be useful to be model free, right? And so what I mean by model free is that, okay, we discussed this, you know, pipeline and state estimation and modeling and planning and control, and we're gonna throw it all away. We're just gonna do end-to-end control, right? And what I mean by that is we're gonna figure out a machine learning model, right? That takes in your inputs, which are your sensor readings, and it's gonna output your controls, right? So you're not gonna have explicit state estimation. You're not gonna have explicit modeling. You're not gonna have explicit planning and controls, right? You're just gonna have something that takes in sensor readings and outputs control. And this seems a little bit wild, right? It's throwing away all of the structure that we had in our system. But the whole point is that in these cases where it's hard to estimate state, it's hard to build a model, it's hard to characterize everything you're going to see, this actually might be easier than building the different pieces, right? And so the whole point of end-to-end model-free control is that you're going to replace that whole pipeline by just a big neural net, right? It doesn't have to be a neural net, it has to just be a function approximator, right? Something that takes in inputs and produces outputs. Okay, so why might this be a good idea? Right? Sounds a bit wild, right? But why might we want to do this? Thoughts?
Apply a lot of logic that you might have.
Right.
It's having it.
So in many cases, how to act is much easier than how to model. And so, for instance, an example I like is you're in a maze, right? You're like trying to get out of the maze. And if you just, in certain cases, if you just go left following the wall, you'll get out of the maze. Whereas if you have to model the whole maze, that's a much harder problem. So in certain problems, it might be a lot easier. I saw a hand somewhere. No, that's. Right. Right. So the nice thing is you're optimizing for what you care about. Like in state estimation and control, you have these little pieces in between, right? So you're estimating state, but you don't care about state. You only care about control, right? So whereas in end-to-end, you're directly optimizing for control. And so you account for all the errors that you would have in the middle. Any other thoughts? Yeah.
With the model approach, you are adding in a lot of things you know currently about the world, but with the model-free approach, you're essentially, I think it's technically more computation intensive because you don't know much about the world. You're effectively adding in a bunch of weird constraints that are not necessarily relevant to the problem, but are needed just because you don't know much about it.
Right. So is that an advantage or a disadvantage? Disadvantage, sure. So some of the advantages here are that you don't have to define the interfaces. Like Sumaya was saying earlier, if you have different models, they compensate for each other, right? So the error is directly targeted, but there's a lack of structure, right? So you often need a shit ton of data, or you need to like find ways to constrain your machine learning model to do sensible things, right? Like for instance, your system should conserve energy. You shouldn't output things that don't conserve energy, but it often there's no reason for the models to do that unless you put structure in it. And so the model-based method is more generalizable, but it's often biased, it's often wrong. Whereas the model-free method, in the limit of infinite data and computed time, will be correct, but it needs infinite data and computed time. So that's kind of the trade-off. So don't do things blindly model-based, or don't do things blindly model-free. Like most systems will be a combination, right? And so kind of the structure of our class is going to be, we're going to start with doing state estimation from Monday, right? We're going to cover system design today. We'll do filtering, localization, and Islam. We'll next cover controls, right? So we'll do feedback control, CID control, MPC, LQR. We'll do planning, search, heuristic, motion planning, and then we'll do learning, imitation learning, reinforcement learning, and so on, right? So yeah, that's gonna be, the structure, we'll hopefully color in all these boxes. One quick note, I'm not here this Monday, but, my postdoc will be giving an excellent lecture, much better than mine, so you all should attend. It'll be fun. And please do attend because it's the basis of the next 5 lectures, so it's an important, yeah. All right, have a good weekend. Thank you.